This video will demonstrate how to write a linear function that models data. To write a linear model, it sounds intimidating, I know. We're really just thinking about writing a linear equation in the form y equals mx plus b. And to do that, we have to know two things, just like if we were writing an equation that was dealing with just given points and slopes. We must know one point, and we must know the slope. In application problems, the slope is often referred to as a rate of change. And for a given point, this is not always the case, but it is often the case that we know an initial value, or like a base phi. Not always, but often the case. The hard part is figuring out, what the unknowns are and how does the information in the problem give you this specific information that we need. Let's look at a couple of examples. The first example is a county water department charges a monthly base fee for water and sewer of $12.50 plus a volume charge of $12.90 per 1,000 gallons of water used. Write a linear function that models this data, then use a model to determine the monthly water bill for a family that uses 3,400 gallons of water in a month. So what we know is that our monthly charge for water and sewer is this base fee plus a volume charge. Now this base fee of $12.50 is kind of our initial value, right? It doesn't matter if you've used any water or not, you're still going to have to pay this base fee. And then the volume charge is the variable, right? It's $12.90 per 1,000 gallons of water used. So we're going to let the monthly charge be our variable y. Our base fee we know is $12.50. The volume charge is $12.90 per 1,000 gallons of water. So we're going to call x our 1,000 gallons of water used. In other words, that is the slope, right? Our price is increasing by $12.90 for every 1,000 gallons used. So that is kind of our change in y over change in x. Now that we have a function, and we can write it in function notation if we want to, we can write that as f of x is equal to 1250 plus 12.90x. To determine the monthly water bill for a family that uses 3,400 gallons of water in a month, we're going to replace x with not 3,400, but 3.4. Because x is representing the thousands of gallons of water used, we can divide 3,400 by 1,000 to determine the actual value of x. So our equation would be 12.50 plus 12.90 times 3.4. And when we perform that calculation, we get 56.36. So the monthly water bill for this family would be $56.36. Example 2 is Kevin, who weighs about 150 pounds, walks at a pace of about 3 miles per hour. When he walks 15 minutes, he burns 56 calories. When he walks 60 minutes, he burns 225 calories. Use this information to write a linear function that models the number of calories a 150-pound person burns from walking at a pace of 3 miles per hour for X minutes. A lot of numbers going on in this problem, so we need to really dig into it to figure out what the variables are representing and if we can figure out some ordered pairs so that we can come up with a point and a slope to write the function that we need. So notice that Kevin, who weighs 150 pounds and walks at a pace of about 3 miles per hour, that expression comes up 2 times in the problem. And we really don't need to do anything with that. This is really just ensuring that the order pairs that we get are pertaining to the same scenario. And so this is just showing that the 2 pieces of data that we get are going to actually be used to model the exact situation that we need to describe. So we are trying to write a linear function that models the number of calories that a person burns for walking at this particular pace for X minutes. So in other words, if we walk X minutes, we want to see how many calories we burn. So X in this case represents minutes and Y represents calories. So from that, now can we figure out 2 ordered pairs? We know that if he walks 15 minutes, he burns 56 calories. So there we have this correspondence of 15 to 56. We also know if he walks 60 minutes, he burns 225 calories. So that's going to be 60, 225. So now that we know 2 data points for this particular situation, we can actually write a linear function to model it. Recall that we have to know a point, which we know. Then we also need to know this slope. So the first order of business is to determine the slope between these 2 points. Remember that slope is y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. So substituting these values, we would have 225 minus 56 divided by 60 minus 15. We get 169 divided by 45. Leave this for a moment in fractional form. You're going to get a little bit of rounding error if you go ahead and round this off, but we'll go ahead and leave this in fractional form and then work with the formula to get the equation, and then we can write it as a decimal if we need to do so. Now that we have a slope and we have a point, our goal is to write this in an equation of a line. So we need to use the point slope form. Y minus y sub 1 is equal to m times x minus x sub 1. It doesn't matter which ordered pair you use at this point. I would probably use the one with the smaller numbers. We would get y minus 56 is equal to 169 divided by 45 times x minus 15. And if we distribute, we have y minus 56 equals 169 divided by 45x minus 169 divided by 45 times 15. And what I noticed there is that the 15 and 45 have a common factor. So I'm going to simplify that. 15 goes into 45 3 times, so this fraction is really 169 divided by 3. And now if I want to solve this for y, I need to add 56. Now of course I can multiply by the LCD and get rid of the fractions and then solve it for y. If I add 56, notice that I need to get a common denominator, and that common denominator is 3. 56 is really 168 divided by 3. And so my model is really 169 divided by 45x. Negative 169 plus 168 divided by 3 is really negative 1/3. So in decimal form, 169 divided by 45 is 3.76. And then 1/3 is 0.3 as a repeating decimal, so we'll say minus 0.3. And this would be the linear function f of x equals 3.76x minus 0.3.